Hello, everyone. Today we're going to be discussing section 1.1, functions and function notation. Goals. Today our goal is to do the following. 1, determine whether or not a relation is a function. We're going to do this with A, a formula/equation, B, a table, and C, a graph. 2, evaluate a function and compute its input/output values. We are going to do this with a formula and equation. We're going to do this with B, a table, and we're going to do this with C, a graph. 3, determine if the function is one-to-one. We're going to do this with A, a formula and equation, B, a table, and C, a graph. And goal 4, we're going to recognize the toolkit functions. What's a function? We can define a function as follows. A rule for a relationship between an input, independent quantity, and an output, dependent quantity, such that each singular input can yield at most one output. When we're asking, is something a function, what we're really asking is, does one input give at most one output? Functions can be expressed in 3 main ways. 1, an equation or formula. 2, a table or collection of ordered pairs. And 3, a graph. We can define a one-to-one function as follows. A function where every output has exactly one input mapped to it is a one-to-one function. When I'm asking, is something one-to-one, what I'm really asking is, does each output come from a unique input? There can be some serious confusion between whether or not something is a function or it is one-to-one. I'll demonstrate the subtlety with what's called a function diagram. We have 2 spaces, one of which is called the domain, one of which is called the range. In the domain space, suppose we have 3, and in the range space, we have 4. If we draw an arrow from 3 to 4, and we call that mapping F, then the piece of information we have is F of 3 equals 4. Similarly, if I put -5 in the domain space and 9 in the range space, and I use that same red arrow mapping, taking us from -5 in the domain space to 9 in the range space, we have the information that F of -5 equals 9. Is this mapping a function? Well, each input has only one output, so yes. Each object in blue has only one target in green. When I say in blue, I mean the domain. And when I say in green, I mean the range. Is this relation one-to-one? Each output has a unique input, so yes. Each object in the range gets targeted only once. Now we have our domain space and our range space again. For lack of confusion, our domain space is colored in blue and our range space is colored in green. So if I use the language blue and green, that's regarding the domain space and the range space, respectively. If I have 3 in the domain space and 4 in the range space, if I have 1 in the range space, let me back that up. If I have 3 and -5 in the domain space, and in the range space, I have 9, 1, and 4, then I'm going to have a mapping where I have 2 arrows coming out of 3 in the domain space, and they are going to 9 and 4. I also have an arrow coming out of -5 going to 1 from the domain space to the range space. I now have the information F of 3 is 4, F of 3 is 9, and F of -5 is 1. Is this a function? The input of 3 has 2 outputs, so no. 3 has 2, we'll call them targets. Is the relation 1 to 1? Each output has a unique input. So yes, all 3 objects in green, the range, are only targeted once. Now we'll go back to our domain space and our range space. We'll examine a different mapping. Suppose in the domain space, I have 3 and -5. In the range space, I have 9. Suppose 3 and 5 both have red arrows starting from them in the domain space to 9 in the range space. Then I have the information f of 3 equals 9 and f of -5 equals 9. Is this a function? Each input has only one output. So yes, each object in the domain has only one target in the range. Is this relation 1 to 1? 9 doesn't have one unique input, so no. 9 is targeted twice. Now we will talk about table representations of functions. Examine the table for a given relation. I have a table with 2 rows, one labeled in, one labeled out. In the in row, I have -1, 0, 1, 2, and 4. In the out row, I have 3, 1, 2, 3, and 5, respectively. Is the relation a function? The question I'm asking here is, does every in have at most one target in out? If I redraw this as a function diagram, in my domain space, which I color blue, I have -1, 0, 1, 2, and 4. In my range space, I have 3, 2, 1, and 5. -1 maps to 3 from the domain to the range space. 0 maps to 1 from the domain to the range space. 1 maps to 2 from the domain to the range space. 2 maps to 3 from the domain to the range space. And 4 maps to 5 from the domain to the range space. Again, the question is the relation a function? Does every in have at most one target in out? This is totally a function. There's only one output per input. Is this relation 1 to 1? Well, in keeping with our diagram from a second ago, what I'm really asking is, does every out get targeted only once? We see the 3 in the range space turn red, signifying that there are 2 values targeting it. This function is not 1 to 1. The out of 3 has 2 values targeting it. If the relation is a function, this is letter C. If the relation is a function, let in be x and out be k of x. Compute 2 times k of 0 minus k of 2. If I think of the equation 2k of 0 minus k of 2, what I'm talking about with k of 0 is the output of our table, our y value, our dependent variable, where our independent value is 0. So k of 0, I look at my table for, I have a circle around the coordinate pair 0, 1 on the table. Since 1 is the input, or I'm sorry, since 0 is the input, then 1 is the output. So k of 0 equals 1. So 2 times k of 0 is equal to 2. So I have 2 minus k of 2. Now I go back to my table and I put a circle over the coordinate pair 2, 3. 2 is the input, so 3 is the output. So k of 2 is equal to 3. So now in my original equation, I have 2 minus 3. That is equal to -1. So 2 times k of 0 minus k of 2 is equal to -1. Part D, I'm asking you to solve for k of x equals 3. What I'm really asking for here, the question, is what are the x values with a y value of 3? So now I'm looking at the table and I have a circle over the first y value of 3. The x value associated with that is -1. So x equals -1. I have another y value of 3 with the associated x value of 2. So x equals 2. Those are the solutions to my equation, k of x equals 3. Now we will examine the table for a given relation. I have a table with 2 rows in and out. In the in row, I have 1, 2, 3, 5, and 2. In the out row, I have 2, 4, 6, 8, and 9. The first question I'm asking is the relation a function? The question I'm asking is, does every in have at most one target in out? If I draw my domain and range spaces, again in blue and green respectively, I have 1 mapping to 2 from the domain to the range space. And I'm using a red arrow for that mapping. In the domain space, I have 2 mapping to 4 in the range space. Again, red arrow mapping. In the domain space, I'm mapping to 6 in the range space, red arrow mapping again. And 5 in the domain space is mapping to 8 in the range space, red arrow mapping again. And the final mapping, I have 2 from the domain space mapping to 9 in the range space. Again, the question I'm asking is, does every in have at most one target in out? Observe that the 2 in the domain space has turned red. The reason for this animation is that we see 2 arrows going out of 2 into the range space, into different values in the range space, in particular 4 and 9. This is totally not a function. There is not only one output per input. Suppose we use this table to plot out points on the XY plane. So here I have a graph. It is a blank grid, which is real numbers by real numbers. This is called a Cartesian plot. I have the X value and the Y value clearly present. And what I'm going to do is take each of the coordinate pairs, 1, 2, 2, 4, 3, 6, 5, 8, and 2, 9. And I'm going to plot those each onto the graph. And I'm going to do this one at a time. I'm not drawing any lines between these points. I'm just allowing the points to exist on the grid. We already know that this isn't a function because of in the in of 2, there's 2 different out values. Okay. How can we make this inference from looking at the graph? Well, if we look at where all of these points are plotted, we see that the offending in is 2, and it's got 2 different y values. I make 2 clear on the grid, on the x-axis. If we draw a horizontal line through x equals 2, we see that we touch 2 different coordinate points, in particular, 2, 4, and 2, 9. This gives way to the vertical line test, in that if a vertical line passes through a graphed relation and captures more than one point, then the relation isn't a function. Here I've got a picture of a graph of a cubic function. It has the x-intercepts of 0, -2, 0, 1, and 0, 3. To the left, as x approaches negative infinity on the x-axis, y approaches negative infinity, and to the right, as x approaches infinity, f of x approaches positive infinity. Is the graphed relation a function? I draw a horizontal line at -2.5, and I see that I only touch the function once. Then I draw a horizontal line at x equals -0.75. I see that I only touch the function once. I draw a vertical line at x equals 1. I only touch the function once. And I draw a vertical line at x equals 2.8, and I only touch the function once. These lines were all drawn at random, and they were meant to display a pattern. It's not difficult to see that no vertical line drawn will intersect this relation more than once. So we would say that this function passes the vertical line test. Thus, it is a function. Now I've got a parabola. This parabola is major to the x-axis. It has its vertex point at 0, 0. Question I'm asking is the graphed relation a function? I'm going to draw a vertical line at y equals, let's see, 1.9, and I see that I intersect this relation twice. Seeing that this relation fails the vertical line test, even if it only fails once, then there is at least one output with two unique, or there is at least one input with two unique outputs. Thus, it is not a function. Now I have a table. In my in row, I have -1, 0, 1, 2, 4. In my out row, I have 3, 1, 2, 3, 5. Similarly, let's plot out the points from this table onto the XY plane. Again, I have a blank XY grid, and the point of origin is roughly in the center of the image. I'm going to plot -1, 3, 0, 1, 1, 2, 2, 3, and 4, 5. Those are now plotted onto the grid. We already know that this is a function because it passes the vertical line test. How could we tell if our function is 1-to-1? So we draw vertical lines through each of the points, and we see that we are only going to get 1 point on each vertical line. I'm drawing vertical lines at each of the x values for the coordinate pairs, and I'm seeing that I'm only touching one coordinate pair each line. We see that the offending out is 3, and it's got two different in values. Now, if I draw a horizontal line at y equals 3, I see that there are two coordinate pairs captured on that horizontal line. This gives way to the horizontal line test, in that if a horizontal line passes through a graphed function and captures more than 1 point, then the relation isn't 1-to-1. Here we have a cubic function that is revisited from a previous example. As x approaches negative infinity, f of x approaches, our y value approaches negative infinity. As x approaches infinity, our y value approaches infinity. We have x-intercepts at 0, -2, or I'm sorry, -2, 0, 1, 0, and 3, 0. Is the graphed function 1-to-1? Well, I draw a horizontal line at roughly x equals -0.8. And I see that I intersect the function twice. The y values are definitely -0.8, but the x values are not necessarily clear. The x values appear to be -2.2, and roughly 2. It's not difficult to see that a horizontal line can be drawn, which will intersect this function more than once. So we would say that this function fails the horizontal line test. Thus, it is not one-to-one. The question I'm asking now is this graph relation one-to-one? This graph is the quadratic parabola with x as the major axis. Again, its vertex is at the coordinate pair 0, 0, which is also known as the point of origin. Seeing that this relation passes the horizontal line test, there is exactly one input per output. I draw a horizontal line at y equals -5. I only touch the function once. Then I draw a horizontal line at y equals 1. I only touch the function once. At the line y equals 4, I touch the function only once. And at roughly 7.5, I touch the function only once. All of these lines were simply meant to demonstrate the pattern that this function will clearly pass the horizontal line test. Thus, it is one-to-one. Given the function f of x below, we're going to determine the following. A, we're going to prove that this is in fact a function. The function pictured is an absolute value function. It is shaped like a V, and we have the vertex of this V is at the coordinate pairs 2, -3. That is demonstrated on an XY plot. The V is pointing upwards and touches the x-axis at x equals 1 and at x equals 0.5 and x equals 3.5. Prove that this is in fact a function. We will perform the vertical line test to show this. We draw a vertical line at x equals -0.5. We see that it only touches once. Then we draw it at roughly x equals, 0.25. We see it only touches once. At roughly 1.1, we only touch once. At 1.8, it only touches once. At 3.2, it only touches once. The relation graph passes the vertical line test for all of the x values in the domain of the relation. Thus, it is a function. Is this function one-to-one? Question B. We perform the horizontal line test to determine this. I draw one horizontal line at y equals -1.5, and I see that I touch the function twice. No, this function is not one-to-one. I highlight these two coordinate pairs, which appears to be at roughly 1.25 as an x value, and the other x value is roughly at 2.75. Next, I ask you to evaluate, part C, I ask you to evaluate f of 2. The question I'm asking here is, what is the output associated with the input of x equals 2? We draw a vertical line at x equals 2, and we see that we intersect the function at the vertex. In particular, the y value associated with this is -3. That is highlighted on the graph. So f of 2 is -3. Part D. Now I need to solve for f of x equals 1. What is /r the inputs associated with the output of y equals 1? So I draw a horizontal line at y equals 1, which is highlighted on the graph, and I see that I intersect the function at 2 points. One where x equals 0 and one where x equals 4. I draw vertical lines at x equals 0 and x equals 4 to show these intersections clearly. Our solutions to the equation f of x equals 1 is x equals 0 and x equals 4. Now we have toolkit functions. There are functions which generally serve as the building blocks of the functions we will be dealing with in this course. For now, we only really need to be able to recognize and name these functions. Truth be told, most of these functions should be familiar with you all. There are 9 functions in our toolkit. the constant function, the identity function, the absolute value function, the reciprocal squared function, the quadratic function, the cubic function, square root function, and the cubic root function. Each of these functions were labeled 1 through 9 respectively. The constant function, f of x equals k. In this case, f of x equals 2. I show a picture of an XY grid with the line y equals 2 drawn clearly on the grid. I'm also showing a table with x and f of x as the rows. In the x row, we have -1, 0, 1, 2, and 4. In the f of x row, we have 2, 2, 2, 2, and 2. Just to be clear, while this function shown is f of x equals 2, the constant function can be any constant value. It does not just have to be 2. Next, we also have, or in the next picture, we have the identity function. Here we have an XY grid with a line that is crossing through the point 0, 0, that's our point of origin, and moving at a perfect diagonal throughout the grid. When I say a perfect diagonal, I mean other coordinate pairs on this function are 1, 1, 2, 2, 3, 3, etc. The equation I show is f of x equals x, and I have a table with 2 rows, the x row and the f of x row. In the x row, I have -1, 0, 1, 2, and 4. In the f of x row, I have -1, 0, 1, 2, and 4. In the absolute value function, I show a picture of the absolute value function graphed. It is a V pointing upwards with the vertex at the point of origin 0, 0. The equation is f of x equals absolute value of x. The way that we write the absolute value of x is 2 vertical bars as brackets with x contained inside of it. I have a table with 2 rows, x and f of x. In the x row, I have -2, -1, 0, 1, and 2. In the f of x row, I have 2, 1, 0, 1, and 2. Here I have the reciprocal function. The function graphed is a reciprocal function which has 2 curved lines with a horizontal and a vertical asymptote at y equals 0 and x equals 0 respectively. The equation given is f of x is equal to 1 over x, or 1 divided by x. I have a table with 2 rows, x and f of x. In the x row, I have -2, -1, 0, 1, and 2. In the f of x row, I have -1/2, -1, UND, which stands for undefined, and that has an exclamation point, 1 and 1/2. Here I have the reciprocal squared function. I've got an XY grid, and I have a function that the function depicted is 1 over x squared. The equation is given f of x equals 1 over x squared. I have a table with 2 rows, x and f of x. In the x row, I have -2, -1, 0, 1, and 2. And in the f of x row, I have 1/4, 1, UND, exclamation point, which stands for undefined, 1 and 1/4 respectively. Next, I have the quadratic function. This is a quadratic parabola with y as its major axis. The equation given is f of x equals x squared. I have an x row and an f of x row in a table. In the x row, I have -2, -1, 0, 1, and 2. In the f of x row, I have 4, 1, 0, 1, and 4. Next, I have a cubic function. This is the equation given is f of x equals x cubed. I have an XY grid with a cubic function pictured passing through the point of origin. I have a table with 2 rows, x and f of x. In the x row, I have -2, -1, 0, 1, and 2. And in the f of x row, I have -8, -1, 0, 1, and 8. Next, I have a square root function. I have depicted an XY grid with a square root function shown on its graph. It starts at the coordinate pair 0, 0, which is our point of origin. The equation given is f of x is the square root of x. I have a table with two rows, x and f of x. In the x row, I have 0, 1, 4, 9, and 16. In the f of x row, I have 0, 1, 2, 3, and 4. Next, I have the cubic root function. In the picture given, I have an XY grid with the cubic root function depicted passing through the point of origin, 0, 0. I have a table with two rows, x and f of x. In the x row, I have -8, -1, 0, 1, and 8. In the f of x row, I have -2, -1, 0, 1, and 2. And that is all for today.